I'm really not hit by person. Experience.
Is it your birthday? Happy birthday.
And Seth.
Happy birthday.
Thank you.
Hey, happy birthday.
Thank you. Seth and
Happy birthday. You're ready for Monday.
Oh, I'm still ready for Monday.
Okay, so let me remind you what we did last time I saw you. We did the first section of this, which was a bunch of different applications of integration. The first average values, then like velocity and displacement and stuff like that. Then just interpreting like what it means to integrate some sort of, like in this case, the rate of the population change was this much. Okay, so you integrate that and you get the total change in population. Okay, and then now today we're doing something related to that, which is rate in, rate out problems. So let me read you what that says. One of the most common and important applications for the definite integral involves multiple moving parts. So these show up on the AP test every year. Like this is gonna for sure be there on there, be on there for a like significant portion of it. The way it works is you'll be given some sort of scenario and like people coming in and people moving out, and then you're asked to calculate how many people went in, how many people left, how many people are there right now, etc. And so the way that works is like this. You'll get the final value will be the initial value plus the total number that came in minus the total number that left, which makes sense. And so those will be some integrals. But I think it'll make more sense if we talk about an example and then look back at this. Okay. All right, so at 9 a.m., which we're calling t equals 0, Indianapolis Metropolitan Airport has 1350 people in it. Then for 12 hours, or any time between 0 and 12 hours, people are going into the airport at the rate E of t, which it doesn't tell us what that is, and then leaving at the rate L of t. E of t and L of t are both measured in people per hour. How many people entered the airport between 12 and 5? Okay. All right. So if people are going in at a certain rate, like I don't know, 10 people per hour or whatever, and you want to find out how many people came in over 5 hours, then you got to accumulate all the people that were coming in, the rate of the people that were coming in. So that's why this should be an integral that you're about to do. So, okay, watch this. All right, so for part A, how many people entered the airport? That would be accumulating all the people that were coming in between 12 and 5 p.m., meaning you're going to do an integral from 12 p.m. to 5 p.m. of the people that came in. Okay, all right, okay. All right, so I'm trying to get from 12 to 5. Remember, 9 a.m. was 0. So, yeah, what's up? 3, 8? Yeah, exactly. 3 hours after 9 to 8 hours after 9. Nice. And then what I'm accumulating is the rate of people coming in. So that would be E of t, that's the people entering. Okay, and then for this one, that's all we can do because we're not given what this function actually is. So that's it, that's your answer. Cool. Yeah, we can't do anything else. Okay, B is how many people are in the airport at 4 p.m. Okay, so for this one, you got to do a little tiny bit of thinking. You had 1350 people in it. Then people are coming in at this rate. People are also leaving. So the people there at 4 p.m. were all the people there, minus all the people that left, but plus all the people that came in. Okay, that's what this is talking about. So the people there at 4 p.m. would be the 1350 that were in there, plus all the people that came in up until 4. So that would be the integral from time 0 to time, what time is 4 p.m.?
Yeah, 7.
Right, you're right. Okay, 7 of all the people that went in minus all the people that left. 0 to 7, all the people that left. Nice. And then again, we're not given what these functions are, so that's the best we can, that's all we can do. All right, and then it says write an equation that gives you, well, let me just read it. Write an equation involving one or more integrals that gives the amount of people inside the airport at any time t between 0 and 12 hours. So for this one, you guys have any ideas? So here it was for 7 hours. If I wanted it for any time t.
Would it be?
Yeah, okay, yeah. It's this exact same thing, except instead of a 7, you put a t. All right, so that would be 1350 plus the integral from 0 up to t of e. This is weird. But I guess technically we should use a different letter than t, because we are already using t for this variable. So I'm just going to say x, e of x dx.
Well, it's another.
Because this is telling me to do it for any time t. It actually doesn't really matter. Like if you use the same t, it's implied that people know, if they were to read it, that this is a different t than this one. But just to be like fully precise.
So would it be the same? I don't get why. How are they different? Like how are they different numbers?
Say that again. How are they different than what? Which ones?
How are they different numbers? Because if the t up top would be like how many hours you're trying to get in between 0 and whatever, and wouldn't it be like e and p would still be that same number?
No, let me try to think of how to explain it.
Does that make sense? Should I ask my question in a different way?
No, it makes sense. You're saying this is at the time, and this is the same. We're talking about the same time. Like if we got 4 p.m., we plug in the 4 or whatever.
Yeah.
I know what you mean, but it's a different thing. This is like a.
It's okay. We can move on.
But it's a good question. It's just hard to explain it. This is like. I don't know. We've seen this type of function before with the area so far function way back in a different unit. And we talked about things like this. And basically, I don't know. The way I convince myself, the way I understand it, is that we're integrating some function here. And this variable is a different it's like it's a function of t, and then we're integrating it up until this point.
Oh.
And here, let's say
Wait,
this.
no,
Let's
I
say
get it.
okay.
Because like you put the function in, but then you can only go up to the certain number in the thingy.
Okay, I'm glad that was
I
yeah.
got
That's
it.
enough. Yeah, I thought of a different way just now, but here's what made sense to Bree. We're integrating this function of t, like, I don't know, t squared or whatever, up from 0 up until whatever this is. So if this was a 4, that's 0 to 4, and etc. That's what made sense to Brenna. This would still need to be some, or sorry, Bree. Sorry, I don't know.
Brenna.
Oh, cool.
So like, what I'm saying is these needs to still be some function like t squared plus 7t plus 90, and then this could be some sort of number. And in other words, if this was a t, or sorry, if these were both t's, then that would be strange. That would be like, okay, imagine we wanted to do this type of thing, so we plug a 7 into this t, then this would become an e of 7, which doesn't make sense, it would just be a number, but we're trying to integrate a function. Yeah.
We don't have the rate after.
Yeah, I guess so, yeah. It's actually not a huge deal, like I said, but if you did put a t into here, people would understand, like, they know, oh, this is a different t. But it's just good to have different variables, like, if you already used the t, don't use it again. Anyway, okay, hopefully that made a little sense. Let's do another rate in, rate out. All right, similar thing, between 0 and 5 hours, where 0 represents 12 p.m., the rate that people are entering in minor league baseball stadium is modeled by that function, which is ugly. And then starting at 2 p.m., people begin to exit the stadium at a rate modeled by that function. Okay, E prime and L prime are measured in people per hour. At 12 p.m., there's 412 people in the stadium. How many people entered during the first 3 hours? Okay. So this time, let me not say much. You guys tell me how to find that out.
Wouldn't it just be that function, but then you plug in 3 for the t?
That would be exactly how many people are coming in at that point.
Oh.
But if I want to figure out how many people have come in altogether, then I got to accumulate all of them. Right. But not even that. This is just asking how many people came in.
Oh, okay, then,
Just that single interval, yeah. Okay, good, nice. So that would be from 0 to 3, because it's just the first 3 hours of the people entering. So that would be E prime of t, which I'm just going to write the function. 536.5 e to the negative 0.1 t dt. All right, and then this you can do in your head. It just requires a tiny bit of u substitution and then some writing, or you can do it on your calculator. So let's do it on the calculator. Okay. Here's me doing it on the calculator just to remind you how. I go to math 9, math 9, because that's integrate. And I plug in my function. Yours should look nicer than this. It looks like I didn't even show my work. But here's me plugging in the function. 536.5 times e to the negative 0.1 x with respect to x from 0 to 3. Okay, and there it is, 1390. Oh, you couldn't see any of that, sorry. There it is, 1390.5102, which you can't have 0.5902 of a person, so I just rounded up to the next thing. So let me go back to the Word document. Okay, 1390, that's a 3 by the way. And then, like I said, I just rounded up to the next person. It doesn't tell you to, but tests or quizzes or whatever, you can ask. And the AP test for sure will be careful about telling you where to round. But I'm just going to round to the nearest person, which is that. Okay, B. Now it's this one. How many total people are in there? So I have to account for all the people there, all the people that came in, and all the people that left. So how many people are inside the stadium when time t equals 4? That's the thing Felix was talking about before. So, okay.
So 412.
plus the integral from 0 to 4 of e of x or e of t or whatever.
Nice. I'm gonna write the actual thing.
Oh, or that.
No, it doesn't matter. And then
Minus the integral of 0 to 4. And then that same equation.
all the people that left. Oh, this is weird. This one's an X, this one's an T. So that's weird. I'm gonna make this a T. Okay, nice. And then, like I said, you put this into the calculator and it'll tell you what it is. Usually when a number is this ugly, it'll be on the calculator section of the AP test. And then if we have a non-calculator part, like ourselves, then we will make the numbers nicer. All right. But like I said, numbers this ugly, usually that will mean calculator section. So you put this into your calculator, like I showed you. I don't want to waste your time and show you how to press buttons. But that would be
Wait, what's next to the 5?
a T.
Oh, okay.
All right, you put this into a calculator, you get 1472.5292, which is about 1473 people. Nice. All right, and then part C. Part C is weird, actually. Also, we did something wrong.
What? You're kidding. What did we do
We
wrong?
did something slightly wrong because look at this. It says people don't start leaving, look,
Until 2 p.m.
yeah, until 2, which is 2 hours in.
So it's really 0 to 2.
Or
Or 2 to 4.
2 to 4 is it? Yeah, exactly. So sorry, I should have caught this earlier. But yeah, 0 to 4, that's all good. But this 0 to 4 should be a 2 to 4. Again, because people don't start leaving until until 2 p.m. So 2 to 4, sorry. This number is still good because we just got it on the calculator. Or sorry, I got it from my answer. Okay, and then because of that reason, that's why I'm saying this part is weird, because it says for 0 to 5, write an expression with one or more integrals that gives the number of people in the stadium at time t. So this is kind of weird because you have to kind of split it up between like, okay, if it's before 2 p.m., then you're only counting the people entering, and then after 2 p.m., you start counting the people leaving. So this part is weird. This is more complicated than I think you would see on an AP test. But let's be fully correct and fully, precisely answer the question. So, if I want the equation that will give me the number of people in the stadium at any time, I gotta say, okay, if it's before 2 p.m., then nobody's leaving. So it's just like the people inside plus the people who are entering. So 0 to t of the entering function.
Wait, why doesn't the answer with you change?
Oh, because I just got it from it would change, but I got it from my key, so it was correct then. Okay. So again, if it's before 2 p.m., then this is it. This is all I have to say. So this is it if t is less than 2, or at most 2, I guess. And then after 2, I have to do that, but also count the people leaving. So after 2, it would look a lot like our answer to part B. 0 to t of the people coming in also account for all the people leaving. So 2 to t of the people leaving, which is what? Of this 398 sun. That's if t is at least 2 or greater than 2. Okay, kind of a very weird one, especially if it's the second one you ever see. Most of the time, it'll just be this part that you have to write the bottom part. But in this case, it was weird because people didn't start leaving until after 2. Yeah.
So for these, we're basically just writing out equations. We're not really solving for anything. Because
Yeah, most of the time. I don't know. It depends. Sometimes you might get nicer numbers here, and then
Okay.
we tell you don't use a calculator.
okay.
But most of the time, yeah, you'll be using a calculator. You write the equations that make sense, and then that's it. I'll show you. Yeah, if we ever have time, I'll show you what these look like on the AP test. It's really similar to this. You just have to know what to plug in. Okay, and then I believe that's it for this section. Sorry, I'm trying to get as much in there. Okay. Yeah. Sorry.
Wait, so you don't even need to solve the C?
Yeah, for C it doesn't, like there's nothing to solve. It just tells you what would it be at any time t. It's not specific enough to solve it for a number. Okay. All right, other questions before I move on? All these numbers make sense? Okay.
And since we didn't make the numbers for the equations, then just don't even worry about them. Like just insert them when they need to be inserted and solve for them. Okay.
Right. Okay. All right, so now that's the end of 8.1. Then I wanted to start 8.2 so we can finish it tomorrow. So 8.2 is all about areas between curves, which conceptually is not hard at all. Conceptually, it is a 6th grade problem. If I told you to get the area of this, it's supposed to be a circle.
Should we be writing this down?
I don't really care either way. I'm just trying to show you what the idea is so you're ready for it. If you're trying to get the area of this, what would you do?
You take the area of the square minus the area.
Yeah, area of the square minus the area of the circle. Okay, the area of the whole thing minus the area you don't want. Okay, all right, so now keep that in mind.
I am.
This is, if you wanted the area of this, you would take the area of the square minus the area of the circle. Okay, you don't have to write this down, I'm just trying to get you in the right headspace. So then watch this. If you're interested in getting the area between two curves, then what you could do is, actually maybe I should write it here so that you don't have a bunch of stuff. You're trying to get the area between some f function and some g function. We'll call this g. Yeah, you'd find the area under f, all of this, and then subtract off the area under g, and what you're left with is the area between. That's it. That's what we're doing this unit. So then that's, yeah, okay, so if F and G are continuous between A and B, and F is always above G, then the area between the two is F minus G.
Are there no
The
intranet?
integral of, well, no, yeah, the integral is how you get the area under something, remember?
That's our intranet?
Oh, those are the intro, I thought you were talking about
No,
integral.
no, I said intranet.
Yeah.
That's fine.
Okay, so that's the idea, top minus bottom. All right, for this, here's like a little bit of a tiny proof. The proof was kind of what we just talked about, but if you're trying to like convince yourself of this, it's helpful to draw a representative rectangle. That doesn't also, I'm just gonna write rectangle. With height f minus g, so f to g, that's what this is talking about. Height of f of x minus g of x. And width, some tiny width, like we're used to getting with integrals. You don't have to make this little picture, but just to remind you, remember when we were getting these like with little rectangles? And we said, okay, we want these rectangles to be really tiny in width. Okay, that's what this dx is about to represent, is that tiny width. Actually, that should be a delta x to match this.
And delta is just like another.
Yeah. Yeah, that delta x you should think of as one thing, not delta x, but all one thing, delta x, and that just represents the tiny width that we're talking about. Okay, and then all of this is just trying to represent, oh, that indeed, if you were to do enough of these tiny rectangles, like all along f minus, like all along this little area, then you would get the area that we are interested in, the area of the study. You said you need to think about it, or can I explain something better?
So for this area is given by, we just listen to draw our function for that point.
Oh, the area can then be given by, oh, I didn't even see that. The area can then be given by, well, okay, watch this. The area of a single rectangle would be given by f of x minus g of x. That's the height times delta x, or like the tiny width. Okay, that's the area of one single little rectangle, this guy. But if you do that for infinitely many rectangles, as long as they're small enough, boop, 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 and then you add all those up, that's exactly what we learned an integral is. So that's why it's saying, if you take infinitely many rectangles, you'll end up with the integral from a to b of f of x minus g of x dx. Yeah, that's why this is called a quasi-proof. It's like half a proof. Or it's the intuition behind the proof. Okay. All right, all of this very abstract, very theoretical. Here's how it is. Here's a problem on it. Oh, also this is a good problem because I think I've convinced you that, okay, if both of them are above the x-axis, then sure, you can do the top minus the bottom and that makes sense. But if one of them or both of them are below the x-axis, then it's a good thing to think about, like, will this still work? Top minus bottom, will that still work? So take maybe 30 seconds to think about, should we alter our thing, or will it all still work? Do I still do top minus bottom, or do I do now, like, separate the integrals, or what do I do to get this area? Again, this is talking about the area bounded by this, and these two lines. Trying to find this area. What are you talking about? You said, Kate, you just add them now. Yeah, okay. Beast, that's exactly right. Yes, exactly. So now notice, okay, if I do the top function minus the bottom function, that still works in the case where they're both below or one of them is below the x-axis or whatever, because now this area right here under the axis is negative. So if I subtract off a negative area, then it gets added on. Minus a negative will become a plus. So it ends up working no matter what. So that's a nice thing. You don't ever have to think real hard. You just say, oh, okay, I just do the top function minus the bottom function. So let's do that. This will be integral from 1 to 2 of top function is obviously the parabola, but just to make sure, which one of these is the parabola?
X squared plus 2.
Okay. Minus bottom function is the line, obviously, which would be negative x. Nice. And then we just do that integral. That would give me this area. Here's me simplifying. Minus negative x is just plus x. Then I'm writing it in the normal polynomial way.
Do we
Then-
factor it, or do we not have to?
You don't have to. This just makes me more comfortable. Okay, then antiderivative of x squared is x cubed over 3, or I like to write it like this sometimes. This would be x squared over 2, or half of x squared. This part would be 2x. Okay, then it's a definite integral, so I don't need the plus c because it's just going to cancel anyway. But I do need to evaluate it at 2 and 1. Okay. So let's evaluate it at 2. If I plug in 2, here's what I get. 1/3 times 2 cubed. Yeah, let me just write it all the long way so you don't get confused. Then 1/2 times 2 squared plus 2 times 2. That's me plugging in 2. Then I'm about to plug in 1. But yeah, what's up?
Going back to security, why did we choose that section? The part where we scribbled?
We didn't really choose it. The problem told us that we want to go from 1 to 2.
Oh, okay. Also, wouldn't the width be 1? If it's between 1 and 2?
What are you talking about? What width?
Wait, the width of the section, like that we're putting in graph?
Yes. So you're saying I should change what?
No, I'm just confused. Where did you get 2 from?
Oh,
If it's between, if that thing that you changed is what it's 1.
yeah. Okay. Because we're taking the integral, we're taking the area between 1 and 2. That's why I'm going from 1 to 2.
Oh.
So yeah, you don't have to think about it in terms of rectangles. That was like the intuition for the proof. That was like kind of abstract. Yeah. Sorry, yeah. I'm just trying to. Yeah, that stuff with the rectangles, you don't have to think about it like that. That was just to show you why this integral would work. But yeah, back to integrals, we're going from 1 to 2. That's why. Okay. So there's me plugging in 2, then minus me plugging in 1. That would be 1/3 times 1 cubed plus 1/2 times 1 squared plus 2 times 1. Okay, all right. Then you do all these calculations. Maybe it's good to just do them like once in a while.
For that one, couldn't we just write like 1/3 plus 1/2?
Yeah, I thought about doing that, but I didn't want to
I
confuse
get why
anybody.
you did it.
All right, then do you want to do this calculation or should I just tell you? All right. If you were to simplify this with fractions and everything, okay, you plug in all this stuff, you simplify it, and you get 41/6. So the area right here is 41/6. One thing I should say is that this is talking about area that we know and love. So if you ever get a negative answer, you probably did bottom minus top or something. So this area, like no negatives can be allowed. It should always be positive. Okay. 214. Yeah, let's do another one. And then we'll be done.
What did you really know? Did you?
All right, so this one, you have to make your own graph. So watch this. Sketch the region bounded by the graphs of that, and then find the area between it. So for this section, I think what people will struggle with is like graphing and like remembering parent functions. Not so much the calculus. Okay, well, yeah, let's do it. I don't know what I want to do first. I think what I want to do first is say the following thing. So watch this. It just tells me to get the area bounded by these two graphs. It doesn't tell me between 3 and 7 or anything like that. So that means that these two graphs must enclose some sort of area. They must intersect the 2 points and make some sort of shape already by themselves. Okay, so how do I know from where to where I'm going? Well, I got to find out those 2 places where they intersect and make a shape. Okay, so first is find the intersection. Find intersection of these 2 functions. It's an O. All right, you guys remember anything about finding intersection?
Can we put them on the graph and then find?
Well, sure, that's one thing. You could graph this one, see where they cross. All right. Or if you don't want to be that precise about this graph, which I don't know what it looks like, just remember how to do it algebraically.
But they equal each other.
You're a beast. Yeah,
Oh,
set this
really?
equal to this. You're trying to find out where they're equal to each other, where they're going to cross. Okay, so set one equal to the other, then solve it. In this case, we're lucky. Watch this. 2x and 2x will cancel once you subtract 2x from both sides. And then here you have a choice. You could factor this, like subtract the 4 over the 5 over and factor it. Or you can just do it normal because there's no extra x term, so you don't have to factor it. So let me just do it normal. Let me just subtract the 1. Oh, what's up?
Oh no, I got the.
Oh, what is it?
X equals 2.
Yeah, so if you subtract the 1, you get this is a 4, which is however you got this. That x should be 2. And then also, don't forget, it can also be negative.
Oh yeah.
Which should make sense, right? This was the intuition that they should intersect in 2 places because that way they like enclose some sort of area. All right, cool. And so the reason this is nice is because now watch this. Okay, let me graph this one because I know for sure what it looks like. So if I graph 2x plus 5, hopefully you remember that's a straight line, mx plus b. It's a straight line with a y-intercept of 5 and a slope of 2.
That's so basic.
You will.
Shoot.
What?
Okay. There's my G in black. And then the nice thing about doing this first is that now I don't have to be super precise about this. Like I don't know exactly what this will look like, but I know it's a parabola pointing upward because it's positive. Okay, and I know that I should cross this line at 2 and negative 2. So I should hit it here. Whoa. Okay, I'll hit that line there, and I'll hit the line here. And so my parabola will look like, it does not really matter. It'll look something like this, though. This is badly calibrated, but it'll look something like this. And now I'm trying to find this area. Okay, all right. So there you can see, like, I did a lot of approximations. I don't know what this parabola actually looks like, but it doesn't matter. This just tells me, okay, what's on top, what's on bottom, that's all I really need. And actually, I thought about it today, you don't even need to know what's on top and what's on bottom. Because if you flip it, if you do bottom minus top, you'll just get the negative of the answer. It doesn't actually matter. If you get the negative of the answer, just flip it, make it back positive.
Wow,
And then you don't have to think that hard. But anyway, this said to sketch it, so we did. All right, now we find the area between those two. Okay, let me not say much. You guys tell me, how do I do that again?
The integral.
Say that louder.
No.
Integral between -2 and 2.
Okay, so that was me finding the interceptions. Let me close that off. That was side work. Then now integral between -2 and 2, nice.
Of x squared plus 2x plus 1
Okay,
minus 2x plus 5 dx.
nice, nice, nice. Yeah, one minus the other. Just to be fully accurate though, remember that it has to be top minus bottom, and the top seems to be the line.
Oh,
So it has to be 2x plus 5 minus the parabola. Again, if you did that on a test, you would see, oh shoot, I got a negative answer, but it doesn't matter, just flip it and make it positive, and that's still the answer. But okay, let me be consistent. Top was the line, so 2x plus 5 minus bottom. And then make sure that when you're doing this minus part, that you put parentheses, because you're subtracting off all of this, not just the first part. You're going to miss negatives if you don't do it. X squared plus 2x plus 1 dx. Okay, and then now this is just an integral that like we know how to do. So let me do it fast, maybe even skip to the end in a second. If I were to simplify this, watch this. 2x minus 2x, these would cancel. And I'd be left with negative x squared plus 4. Again, 2x minus 2x went away. Negative x squared here, and then 5 minus 1 is 4. So that's how I got that. Okay, you integrate this, you would get the antiderivative of this is negative 1/3 x cubed. Or you guys maybe like x cubed over 3, it doesn't matter, same thing. Plus 4, plus 4x. Then I'm evaluating that at 2 and negative 2. Okay, all right. So you plug in your numbers. That's me plugging in 2 minus, this is me plugging in negative 2. Okay, and then on your homework or sometime when we have more time, I would let you try to simplify this just so you get used to it, you're good on tests and quizzes and stuff. But I don't think we're interested in doing that. So you do some of this arithmetic and you get 32 over 3. Okay. Yeah, all right, and then now we have 10 minutes left, so I don't know if it's worth doing another one. Maybe you guys can try another one if you'd like, but we'll pick up on the rest of this next time.
Why is it so